So far, we have been dealing with particles and what happens to particles when you have forces acting on them and so on, right? Now what we are going to do is to focus on system of particles. So that means you're talking about lots of particles that are distributed. For example, if you take this scale, now this scale has masses distributed everywhere. It's a continuous distribution. Sometimes you may have discrete distribution. You may have one object here and another object there, right? So you have a bunch of particles that make up the scale. But we can treat this entire thing as if it was one point, it was concentrated mass at one point for certain purposes. For everything you cannot do that, right? So for example, you can't say that this entire thing is actually a point mass. You can't say that, but for certain purposes you can. Like for example, if I'm trying to see where I should exert a force, now there is gravitational force acting here, acting there, acting there, acting everywhere. Now if I try to hold it at this place, it is going to fall off, right? But there is a place where I can hold somewhere there where it does not do all this turning around, right? So in fact, if I try to hold it here, you can see that there is one place where you can nicely hold it. That point, we call it the center of mass. Well, in this particular case, it's called center of gravity because you're holding it like that. But in general, you will call that point center of mass. You can also see it. If I throw this up, watch as it's going up. Can you see that there is this one point that just goes up and down? The rest of it looks like it is turning around. So let me show it again. And if I do this projectile motion kind of throw like that, you can see that this one point comes out that way. So there is this idea of center of mass that we probably already are familiar with. And what we are now going to do is to formalize this idea. It is an imaginary point, and that's something I want you to keep in mind. So imagine that we have a coordinate system like this, and I have one object sitting here, a second object that is sitting there, and a third object sitting there. Let me call all these things as point masses. So this fellow has an x coordinate, x1, y1. This one has an x coordinate, x2, y2. This has x3, y3. This is the origin. Can we think about some sort of an average position of these three? Well, usually we would have called some point here as the average position. So if, for example, all of these were the same mass, I would have written the average position as x1 plus x2 plus x3 by 3. This I would have called as some sort of average x value, correct? X average, let's write it like that. But that is valid if there was one object here. Suppose there were two objects here and one, then I should count this x1 two times. So I should do a weighted average. But now instead of objects being there, I have a mass m1, and here I have a mass m2, and there I have a mass m3. Okay, but now m1 may be much larger than m2. So you should count this much more than you should count that. How much more? So this formula is not going to work. So instead what is going to work is you should say this should be counted m1 times. So we'll write it as m1 x1. So that means you count x1 m1 times, and then you count x2 m2 times. So we call this weighted average. The weighting is done by the mass. So you give that much weight to this as its mass. More mass, more weightage. Okay, plus m3 x3, m3 x3. But now what do I divide this by? If, for example, I had two masses here, one, let's say 2 points here, 1 point there and 1 point there, I would have counted it as 2 plus 1 plus 1, 4, right? But now I have m1 points. Imagine that you have m1 kgs. So 1 kg you should think of as 1. You have m1 kgs, m2 kgs, m3 kgs. How many kgs do you have? m1 plus m2 plus m3. So m1 plus m2 plus m3. This is the sort of average position. Now instead of calling it average position, because average is not a very well defined quantity, we call this the center of mass. So x center of mass is m1 x1 plus m2 x2 plus m3 x3 by m1 plus m2 plus m3. If I have n objects, then you will write it as m1 m, right? You will write m1 x1 m2 x2 m3 x3. You keep adding it all the way till mn xn. What do you do with y? Same thing. So y center of mass will basically be the average of all the y's, except you are going to add m1 y1, m2 y2. Now it becomes boring to add it like that. So we say mi yi, and you do a summation. So this is a symbol to say add it from I equals 1, 2, 3 and so on, divided by the sum of MIs. What is the sum of MIs? Total mass M. Okay. What is interesting is the total mass times Y, center of mass, is M1 Y1 plus M2 Y2 plus M3 Y3. That's very, very important and useful, because that tells you that in some sort of way the whole mass is sitting at this place. Okay. Now we have used X and Y, but I could have also used R. I could have said let this be R1 vector, R2 vector, and this is R3 vector, and then I can talk about R center of mass, right? And then we will write R center of mass vector is M1 R1 vector plus M2 R2 vector plus M3 R3 vector by M1 plus M2 plus M3, right? So we can write that in a shorter form like this: summation of Mi Ri vectors by summation of Mi's, which I will just call it total mass. Okay. So this is the definition of the center of mass, position of the center of mass. Notice that I have an origin. It is very important to have the origin, and always select the origin as a known point before you start the calculation, because you're calculating from the origin. Okay, let us come back. So the idea here is that this is a calculated point. It is an imaginary point. Is there anything at this place? Not really, not necessary. Okay, this is a point that you just calculated. It represents some sort of an average point. Why is this even important? Now you can't use the definition to figure that out. You have to start looking at the definition, applying it, and seeing whether this leads to anything useful. Trust me, it does become very, very useful. Okay, all of our physics laws turn out to be extremely useful around the center of mass. So there is a good reason for why we should talk about the center of mass. For now, we will just calculate the center of mass. Later you will see how useful it turns out to be. Okay, now what I have done here is I have used all of these fellows as continuous mass, discrete points, right? But if I take a scale, it is continuous. If I take a disk like this, right, you see that the mass is distributed, it is continuous. So what happens if the mass is continuous? Then how will I find the center of mass? So let us look at that now. Now let us take something that looks like this. It's a continuous distribution of mass. Okay, so if I take this point, I am going to call this point R1. Okay, now this particular place has some mass. At this location, I should be calling it small mass, so I'll usually call it dm1. Okay, now let me take this place. I'm going to call that R2. Right, so there is a small little tiny portion here, and it has mass dm2. So, but if I did this for all the points, it's a lot of addition that I have to do, right? But for each one, if I try to do the same kind of calculation, I will be writing dm1 into r1 vector. This is a vector, this is a vector. So I should be multiplying by r1, but usually you take the r1 and put it on this side. So we'll write r1 vector plus same thing r2 vector dm2 plus r3 vector dm3. But this is very, very long because you need to do this for infinite number of points. So we do a continuous addition, and so we write this as integral Ri dmi. So you should write it like this, Ri dmi, where I goes to infinite number of points. But usually we don't write it this way. We know in this summation we write mi Ri because we want to say it is the ith mass and it is the ith position. Ith mass position, the position of the ith mass, right? So first mass, second mass, third mass. Here we know that it is understood. It is the R of the dm, or it is the dm of that R. So there is a connection. So just by convention we don't draw or we don't write that I. So when we say R dm, it doesn't mean everything has the same R. Pick an R. That R would have a small mass there at that location, which we will call it dm. So whose dm is this? It is the dm located at R. Now you have to integrate, or you have to add. This integral just simply means summation. Okay, it is just a S. S is standing for the sigma summation. You are adding this up over all points where there is mass. All points where there is mass. How we add it up is exactly what we are going to learn when we solve problems. But the key idea is that you are basically saying pick a place, pick an R, at that R there is some mass, dm times R vector. This is an R vector here. Okay, so that's important. Now what is this calculation? This is going to tell me total mass, which is integral dm times R center of mass. Right? It is as if it is concentrated at this location. So you take the entire mass and put it there, which is just simply adding up all the masses. So we write it like this. We say R center of mass for a continuous system is integral R dm, integral R vector dm by integral dm. You can call this total mass. Okay, where these integrals are done over all the places where there are masses. Okay, now what does this mean? For example, if you take x, for xcm, you can write, if I take the xcm, this is going to be some xcm I cap plus ycm j cap and so on, right? And then zcm, I'm not writing that. But this also is going to be R vector, which is x I cap plus y j cap dm. But you know that I affects I and not j. So that means you can take the I component separately and you can write xcm must be integral x dm by integral dm. Is that okay? So you can use this, and similarly you can write that for y is integral y dm by integral dm. So this is very, very important and useful because this tells you how to calculate the center of mass for continuous objects. Now many times, if for example I take a rod which is nice and uniform, you know that its center of mass is going to be right at the center. You know it by just looking at it, right? So if I take this scale, I know that the center of mass is not here. If I try to hold it here, it's going to come down. I know its center of mass is here, right? But what if it was not uniform? Well, if it's not uniform, you have to find it using this. You can't guess it. If I had a disk which was uniform, I know its center of mass is at the center. But if it was a disk which was not uniform, let us say that this side had more mass than that side, well then you have to calculate it by using this integral. Okay, is that idea first clear to everybody? So now let us focus on how do I calculate center of mass of different kinds of systems. When we do a couple of questions, we'll get an idea. Remember, first, the most important point, choose the origin. Whatever you do, choose the origin as a known point. I will later show you what are the other important things to keep in mind. But choose the origin as a known point. Second, remember that center of mass is an imaginary position. Okay, center of mass is imaginary. It's a calculated quantity. So we will come back to some more points later. But this is extremely important. Why am I saying this? Because often what happens is people try to say, let the center of mass be the origin. But if you say center of mass is the origin, here I know that this is the origin. Center of mass is what I'm trying to find. If you say center of mass is the origin, it looks nice because after you do the calculation, this answer is going to be 0. But to do this calculation, I need to know what is that R vector. To know what is this R vector from a place which is not known, which means you have to find this vector. Now that is known, this is known, this vector is known. But if I assume that to be the origin, that means I need this vector. How do I know, how do I find a vector from some point that I don't know? Messy. You could do it, but it's messy, right? Nothing stops you from choosing the origin as the center of mass. But my suggestion is for most problems, don't do that. Sometimes people do that, books do that. Okay, it's a good idea to choose the origin as a known place and then calculate the position of the center of mass.